There are a couple ways to calculate confidence intervals, and in this video we'll look at a parametric method using the standard error. Our dataset comes from Rebecca Warner's textbook, Applied Statistics, the second edition. We have 130 heart rates that will serve as our population of interest, with a mean of 73.8 and a standard deviation of 7.06. We created 4 random samples of the data of varying size, 9, 30, 65, and then we took 500 samples of size 9 and averaged their means. Then we create a function that will give us descriptive statistics for each of these samples. When we compare these samples, a few things stand out. As the sample size increases, the means get closer to the population mean, and the standard error and the margin of error decrease, which means our estimates become more precise. Now here's the formula for calculating the standard error and a confidence interval from it. The standard error is the standard deviation of the sampling distribution for the sample means. Now in reality, we don't take 500 samples and average their means. Instead, we estimate it with the standard deviation of our random sample divided by the square root of our sample size. And as our sample size increases, the confidence interval narrows or becomes more precise. The standard error multiplied by our test statistic, here the z-score, is our margin of error. So if we want a 95% confidence level, we use a z-score of 1.96. Remember that 95% of a normally distributed population is within 2 standard deviations of the mean, or more precisely 1.96. The confidence interval is the sample mean plus and minus the margin of error. Let's take a little deeper look at how the standard error works. The standard error is a form of the standard deviation, but it serves a different purpose. The standard deviation is a descriptive statistic that estimates variability. The standard error is an inferential statistic, which measures the precision of the estimates of the population from a sample. Now, the reason we can estimate population means within a confidence interval from a single random sample is found in the central limit theorem. The central limit theorem is vital for 2 main reasons: the precision of the estimates and the normality assumption. The fact that sampling distributions can approximate a normal distribution has critical implications. You can have data that isn't normally distributed, but if your sample size is large enough and your sample is drawn well, it's random, the central limit theorem applies and you can use parametric tests. Let's modify our data set to show how this can work. We'll create a random sample of 66 new heart rates that range from 42 to 65. We'll imagine that they were sampled from marathon runners. Now let's subset the highest 67 heart rates in our data set, which will give us a skewed distribution when they're combined. Our population distribution is now no longer normally distributed, but we'll use the same sampling technique as before. We'll take 500 samples of size 9 and average their means. It's a close approximation of the population mean. Providing the assumptions are met, the sample is random and the sample size is sufficient, which is normally 30 or more for somewhat skewed data sets, we can use the standard error to estimate population means within a confidence interval.